Okay, students, we move now into chapter 9. This is exciting. This will be a very brief chapter. It's very straightforward. We're going to talk about transformations. So I would start by asking people what are rigid motions, and typically someone is able to remind me that doesn't this have something to do with congruence? Yeah, that the idea is two shapes can be considered congruent if everything about them is the same. And the only thing that actually separates them is some combination of rigid motion. So this would be a rigid motion over to the right and then up, right? This is a rigid motion where you take this and you just sort of like rotate it, right? You go like this. They do not affect the actual measurements. It's things like dilations that lead to similar shapes, but they haven't been moved through a rigid motion. So we're going to learn about all the different types of rigid motions, and we're going to talk about having a pre-image and an image, not an image and a post image, which I think for some of my students can really confuse them. So the idea is like this chapter, if I start you off with a triangle and the goal is for you to move it to the right, and then it's a new triangle, we consider this the pre-image because it's what you started with. It's not really your answer. So it exists in the previous tense. Like it already existed, and then it becomes the image. It becomes your answer. So the change is what causes it to then be our image, as opposed to image having an image and then turning it into a post image. They don't have us do that. I don't make the rules, so you got to understand. Pre-image is what you start with, image is what you get. And a translation is the first thing that we're going to learn about, where we're going to move every single point in the same direction, in the same measurement. So we're going to use what's called vectors. You're going to take a point and apply a vector and apply the same vector to every point such that all the vectors run parallel to each other and that these points are like collinear. And you can see we start with points P and it becomes P prime. We have Q and it becomes Q prime. And it's those prime points that are used in the image. So translations is a very straightforward process. You apply a horizontal vector, you apply a vertical vector, right? The vertical vector is obviously going to be affecting the y. How much are you moving the points up or down? The horizontal vector, that's going to be affecting left and right. So when I see +3, everybody's moving up 3 from -1 to 2, from -1 to 2, from 4 to 7, from 4 to 7. And then vertically, everybody's going down 1, from 2 to 1, from 5 to 4, from 6 to 5, from 2 to 1. And we can see from C to C prime is down 1, to the right 1, 2, 3. So we can literally count our way there. We can just count. Vectors are easy money. The rule is you just follow these rules right here. Add 3 to every x, subtract 1 from every y. So now we get to the point where we get to start trying this stuff on our own. While we're living in a world of COVID, we're probably going to want, like, not everyone has graph paper at home. There will be lots of opportunities for me to really just ask you guys about these rules, for me to really just say, listen, what would these new points be if you apply these rules? So I might not even make you do a lot of graphing, but if I can say, can you tell me what does S become when it becomes S prime? And for you to say, well, it's X plus 1, so 6, and Y plus 2, so 4. So S prime would be at 6, 4. We're learning a new vocab word today. We're not really going to use it much, if I'm being honest, but an isometry. It's a transformation that preserves length and angle measures. So an isometry is literally just replacing congruence. So when you go from here to here and you go, hey, that triangle ABC is congruent to triangle A prime, B prime, C prime, you go, yeah, that's because we just created an isometry. So an isometry is an action. Well, when we're creating an isometry, that's an action. An isometry is a transformation that preserves. So when we perform a translation, that translation qualifies as an isometry. So I already mentioned vectors as being like, so I mentioned like we do a horizontal vector and we do a vertical vector, and that creates a diagonal vector. So a vector is a quantity that has both direction and magnitude. So you're going x direction in x magnitude. So it says that a vector takes us from our initial point to the terminal point by using a horizontal component and a vertical component. That doesn't mean, like, this is technically a vector. It just is one where it has a horizontal component of moving to 5 units to the right and a vertical component of nothing. It doesn't go up or down. So like you can consider anything a vector. It doesn't have to be diagonal to be considered a vector. But we learned this awesome little new way to sort of write vector rules, where instead of saying x plus 5, y plus 3, with the parentheses, you use brackets and go 5, 3. And that this and this are the same thing. So it's a nifty little new way to write about things that will definitely be a big part of this chapter. It's just writing stuff as a vector, which I think is great. Okay, so I'll let you maybe pause here, look at this for a second. And this pretty much gets us, so we can see here, applying the vector 5, 1. It's like saying x plus 5 and y minus 1. It's the same things are happening. Over 5 down 1, over 5 down 1, over 5 down 1 to every point. So here's our little summary. Vectors allow us to combine horizontal and vertical shifts into one transformation. We call it a translation. This chapter is short. We just need to talk about reflections and rotations, and we're done. So work on today's homework. I hope this video is helpful, and I'll see you guys